So, good afternoon, everyone. My name is Prateem Mandal. I am technical lead architect at MarketShare, and the topic of my presentation today is predictive analytics as a service. A few words about MarketShare first. MarketShare is a leading provider of marketing analytics and decision support. It not only gives you insights of the data, but it also gives you an idea about what the actions you should take next. And we have a suite of products that we use to provide these insights, and our focus is to leverage the product-based delivery to provide high-quality marketing insights at very competitive prices. Okay, so why do we need predictive analytics as a service? Why is MarketShare so interested in it? And what is the approach that we took to deliver it? For that, first let's start by looking at the analytics lifecycle itself. It begins with client onboarding. And what happens here is that TPMs, the project managers, the strategists sit across the table from the client, and they ask questions like, what kind of data sources are there? What are the attributes in these data sources? Why they are interesting? What are the prior beliefs of the customer as to what works, what doesn't work, and what kind of questions the client wants answered? That is the first step. The second step is ETL. Here, the data scientists, the data engineers look at the information gathered during the client onboarding, and they may have to write custom adapters for the data sources that the clients have, and they end up producing the fact tables, some kind of fact tables. The next step is feature engineering, and this is the first step when the modeling begins. And it's a very crucial step because the quality of features directly affect the quality of the model. And what happens in feature engineering is that the fact tables are massaged in some way to produce the feature set. This is used for training the model, which comes next. So in the modeling step, which is generally done by the modeler, we take the feature set from the previous step, and the feature set is a pool of features. It's a whole feature space, and the purpose of this modeling step is to find out a subset of the feature space which is the most predictive one, and end up producing a model which is fitting that that subset of feature with the best coefficients that fits the training set. Okay, so that's modeling. Finally, the last step of the modeling sub-process in this entire analytics lifecycle is to take the model, apply it on the feature set, and get scoring and attribution. The end product of scoring and attribution is some kind of a data cube that is then used for scenario analysis and reporting. All right. So as you see here, it's a complex process. It has many steps. It includes groups of people with very different skill sets and different local goals. Also, there is a lot of nitty-gritty about a particular client that people involved in this process might have to remember. So therefore, it is very easy to get into this trap of developing this entire setup, which is very custom built for every client. Now, if that happens, then this model won't scale on the resources, on the engineering and modeling resources as we add on more and more clients. So that, in short, is the business case for this presentation, and that's the need that justifies the need for predictive analytics as a service. And that's what I'm going to talk about next. Okay, so given that background, what can we do about solving this problem? The standard answer is that if we can come up with a formalism that separates out or abstracts out the common portions of this task into a product and the contextual peculiarities of the client into fixed parameters, then perhaps we can compartmentalize all the custom information about every client into neat buckets and probably scale in both modeling as well as engineering resources. So let's look at that problem and see if we can solve it in some way. Okay, so if we are searching for this formalism, where should we start from? An obvious place to look at is the modeling subflow in this entire flow, because that's the beating heart of the entire system. And I'm going to talk about the subsets that you can see here in the way we have implemented it in MarketShare in the following slides. But what we are searching for here is an API or a language in which a modeler can express his or her modeling problem. The API should be general enough that the modeler is able to express the modeling problem for any client. It doesn't matter what vertical and what are the particular peculiarities of the client is. Okay, so let's look at each of these stages one by one for modeling and see if we can formalize them. All right, so we'll start with the feature engineering first. All right, what you see here is a user history. It shows the marketing treatments that the user was exposed to, and it could be other kind of stuff as well. For example, it could be digital, it could be non-digital, offline. It could be things which are not marketing treatments at all. For example, Christmas or unemployment rate and so on and so forth. But you can look at them and think of them as causes. And that leads to an effect that we are interested in, that we want to understand as to why it happened. And the cause and the effect is linked by the entity, which is the user. So this is, in some sense, the smallest indivisible problem of attribution that I'm trying to represent here. And the claim is that doesn't matter what kind of client we face, the ETL can always represent the data into these three classes. One is the cause fact tables, the other is the effect fact tables, and the final one is the user fact tables. There could be some ancillary tables like mapping tables, etc. All right, so let's look at it a little bit more deeply. So the causes could be, as I said, marketing treatments. It could be digital, it could be offline, it could be past activity, and it could be unemployment rate and so on and so forth. The colors or the patterns that you see, I would use it a lot in the presentation, so I want the understanding of those colors to be very clear. The color you could think of as marketing treatment type, let's say. And what is a marketing treatment type is something that a modeler should decide, because he wants to look at them in a way that they are most classifying, not noisy, not losing information, but just about right. So each of these marketing treatments or causes are, you could think of them as an attribute vector. And to what extent to look into this attribute vector to assign it a type is something which is a modeler's choice. And he can decide on this because he has some domain expertise about a particular vertical or about the client. So that is one of the parameters that we want to abstract out. So in this case, we can see that if you just look at the particular attribute called channel in that attribute vector, then we can see there are 5 different kinds of attributes for all types of causes in this particular example. One is email, another is display impression, another is newspaper, past purchase behavior. That's all. And of course, the search, I'm sorry. Yeah. Okay. So, but if the modeler thinks that, okay, this is not classifying enough, and I want to look at channel and sub-channel, then there could be more patterns into this. So the display impression got broken down into 2 subgroups based on brand audio and brand video, which are the 2 domain values of sub-channel. It could, and you could go more granular, and for example, the search now got broken down into two different subtypes. Okay, so what I'm trying to say here is that there is attribute vector by which you represent each of the data points, and you can look at a subset of this attribute vector to impose the definition of a marketing treatment type. And it's very subjective that a modeler can decide as an input parameter to the system. Okay, so in the end, when everything is over, when the modeling is over, what would happen is that we would be able to take the credit for that effect and assign the portions of that credit to each of the marketing treatments. And that forms the basis of the rest of the reporting and predictive analytics, and we'll look at it as well. But this is what will happen at the end, okay? And that's all that we have to cover. So we have defined the terms. Now let's look at feature engineering. Okay, so we have this single problem at its most indivisible atomic level. And in a real data set, we have lots of such problems. Okay, so there are lots of sequences ending up in either a conversion or a non-conversion, and they have lots of causes preceding them. And some of them are very targeted to a particular user. Some of them are much more general, which covers lots of users, for example, TV ads. The claim is that we can, from here, which is the fact table, you can think of them as the fact table by the ETL, we can go to the feature set in a common way in 3 steps. Okay? The first step is to properly attribute or link these marketing treatments to the user. The second step is to group them by the marketing treatment type or the type of the cause as defined by the parameter of the modeler. And the third step is to apply some kind of a mathematical function on top of each of these groups or multiple mathematical functions to each of these groups to get a pool of features. None of this is custom to any client. This is common. Let me take a specific example to again work through the same workflow. So let's take the example of generalized hazard transform. This is one of the things that we internally use in MarketShare. It's a very simple expression. What it says is that let's say you want to compute generalized hazard transform for display impression. So what you do is that you filter out the display impressions in the list of causes, and you pick out the display impression which is the closest to the conversion, and you basically apply the function 1 upon 1 plus x, where x is that lag of the display impression, the closest display impression from the effect. But it doesn't really matter what kind of feature you can come up with. It is these steps, which is common to all of them, which is to take the list of causes, filter it out, group it, map it up to some values, and finally apply the function and get the value. Okay. So once you're done with this, what you have got is the feature set. And as we have seen that all of the steps here are common, except the one parameter that we talked about is the marketing treatment type. Let's skip modeling. I'll come to it at the end because it's slightly orthogonal. And we can follow the scoring process better if we have the feature engineering fresh in our mind. Let's look at the scoring first. Okay, just to point out that what happened in the modeling, by the way, is that we looked at the entire pool of features and we figured out that subset which is the most predictive, and we also figured out the coefficients by fitting it to the training set. Okay, so we have the model. Let's move to the scoring. All right, so for a given sequence, we can apply the feature set. We can look at the feature set and get the values of each of the features. And again, depending on the modeling technique that you are using, let me take the example of logistic function. We can come up with a way of figuring out the attribution. It is not, again, custom to a client, but it is linked to the technique that you are using. So for example, we can use a technique where we can mute, unmute individual features, apply the logistic regression function, get the conversion probability, and from that we can figure out what is the incremental effect of each of the features. So that could be one of the mechanisms to find out the attribution. But whatever it is, it's common. So let's say that we have the attribution available to us next. And I've just represented it at the bottom where we have the metric or the feature linked to the effect and the amount of credit that we are giving to that feature for that effect. This, in some sense, the scoring is over at this point. From a modeling perspective, the scoring is over. And this is useful. For example, on an ongoing basis, we can use this information to figure out if the model is slipping and if we need to recompute the model. But it is still not good enough for end client for most use cases, because end clients have questions like, what would happen if I move $1 million from, let's say, display impression to paid search? And metrics themselves do not have the attributes which are channel type or event type. Those are destroyed when we computed the metrics from the marketing treatments. So what we need to do is to take the credit that has been given to the metric back to the marketing treatment. So that's part B of scoring. So what we do here is that we took the result from the previous example, and we have to have some bookkeeping which remembers what marketing treatment actually contributed to a particular feature, and then we can take the credit for the feature and distribute it back to each of the marketing treatments in some form. One could be equal distribution, the other could be based on the particular mathematical expression that we applied for that particular feature. For example, in Jihad, we applied it only to the closest marketing treatment, so we can give the entire credit to the closest marketing treatment. But again, this is something which is linked to the particular mathematical expression we are applying, not specific to the client. So we end up doing it, and we drop all the useless information here, and we end up with this table, which is linking a marketing treatment to an effect and giving the credit to that marketing treatment for that effect. This is the most granular attribution information that you can get, and all the reporting as well as predictive analytics use cases could be handled by this particular information. However, this is very big and unwieldy, and therefore it makes sense to roll it up a little bit more for real use cases. So I have again written down the same table. This time I have added the actual attribute vector, and during the onboarding process we know what kind of questions the client is interested in. So most of these attributes are not interesting, so we can drop them, and whatever is left we can aggregate it up, and what we get is a cube. We can add the spend information, which generally comes at a much less granular level, to this cube. And now what we have got is a cube which could not only help in reporting, but what you can see here is that it has the cross section on the left. It has the input, which is the spend, and the output, which is the attribution. This is the value add of the attribution, which we didn't have before. And now we can apply some kind of production function on this to do any kind of predictive analytics. So let's look at some of the screenshots of action, which is one of the products which is powered by this cube. So you can see this is the weekly attribution by date, and we are slicing and dicing by channel and sub-channel. And if the user wants to slice and dice it by channel, sub-channel, and tactic, he can get a higher granularity information out of it. The same report you see by revenue, the attribution of the revenue rather than the conversions. Okay, and this is where we come to the predictive analytics part. So what this one is showing is that there is an opportunity to improve the revenue by 7.3 million from 49 to 56 in the context of the media channel itself. And if you proceed further, what you can see is that what it is recommending is that reduce 0.5 million from brand property of SEM, and 0.5 million from SEM generic, and add some 0.8 million to SEM core brand, which means overall remove around 0.3 million from SEM. Similarly, in display, it is removing around 0.1 million, and it should all add up. Finally, in the affiliate, it is asking to add you at 0.3 million. So, so this is an actionable result that you can get from that cube. Okay, I'll skip over the engineering slides. I'll go to the modeling directly. So as we saw, that modeling is nothing but the problem is crawling through the search space of the subset of the features that is most predictive. And for this, we use a genetic algorithm-based approach. And all we do here is that the entire feature set is the chromosome, and a model is switching on the particular subset of the features that we have selected for that model. And we randomly generate a population of models, and we score them. And 20% of the highest scoring models are allowed to exchange the genetic material to produce offsprings for the next generation. And so these kind of offsprings, which are generated through crossing them over, are called crossed over models. And some of them are mutated with a low probability, which we call mutation models, and the rest of it is randomly generated, which are called new models. So this is an early result, and what you see here is that the best models for every generation come from crossover as expected. Sometimes they come from mutation, but almost never from the new or randomly generated models. In the another view, you can see that we are focusing just on the crossover models, and what you can see is that every generation, the best crossover model scores have generally increased, while the average has also improved, while the variance has dropped. Another view of that is trying to show you that the crossover models, which we expect are the best models, the overall health is improving with time. So the results are converging in some sense. Okay, so that's modeling. So what I've tried to show here is that just by using a few of the parameters, the rest of the modeling process is common, and therefore you can formalize the entire process. Not only does it do that, because you have a formal process, you can automate the entire workflow. And what you can see here is that apart from where we need human intervention, which is onboarding, and we have another human intervention in model UAT, but that is not for technical reason, but policy decision. The rest of the entire workflow could be finished in less than 2 days. And that's very important because it gives us the capability of continuous integration. And we know, even when the modeler is still working on tuning the model, that there are no outstanding issues, so it improves the quality a lot. That's it. Thank you.
Do we have questions? We've got time for a few. Anyone?
I have 2 questions. The first question is, how did you deal with the interaction between the different channels? For example, the email channel may have an impact on the search later. How does your model take into account that? The second question is, based on all your analysis, out of all the different channels, do you see a general trend? Like what percentage people you would recommend to spend on search, and what percentage on email or TV?
Okay, so I'll take the second question first. No, we do not see a general trend, but there is probably a general trend by different verticals. But I'm not aware of what that general trend might be. But across all the clients of MarketShare, there is no general trend. In fact, they vary a lot. I didn't get the first question, actually.
Well, the first question is, when you look at the vector, it's a flat vector, and you have display, search, email, for example, as features for your model.
Okay.
Now, how do you deal with the interaction between them? For example, maybe that search was caused by your email marketing.
Oh, okay. So you're saying that certain effects could be causes for other effects. Yeah. So in fact, it is possible because it is in fact very possible that you have a 2-stage model where you first go to one type of cause, one type of effect, and that effect becomes a cause for the next type of effect. But the abstraction that we showed is applicable to a single stage, and you can apply it multiple times at different stages, if I understood your question right. So the abstraction is not stopping you from applying that kind of a mechanism.
Any other questions? Okay, so let's thank our speaker.
Thank you.